G'day everyone and welcome back to my channel. So last couple of days ago, I should say, last time I was talking about this, I was explaining that I'd add this transistor here in series with the reference, which runs off a floating supply. I should probably point that out. Because otherwise people would be looking at it going, well, hold on, that's referenced back somewhere here. No, it's not. It's referenced just where you can see it. So I added this transistor in here, biased it on from this regulated supply that also biases the output on, that the comparator transistor pulls down to the output. The reference is adjustable. The reference goes again between the positive output and the base of this comparator transistor, which is pulling down the series pass element to the negative terminal. That way you can sense the voltage drop across both terminals. If you just connected this to the incoming negative, you wouldn't sense the voltage drop across this wire. So I added that transistor, biased it on. That doesn't affect regulation. It works perfectly. That allows the current to flow like it should. Well, here's the problem. I might have screwed something up. I might need to turn this transistor around because the reference is in like anti-parallel to the way you normally turn a PNP on, because it's comparing this voltage against the output voltage, so that gets added to the output voltage in reverse. That makes sense. I haven't wrapped my head around that yet. But anyway, I added another transistor to then pull down the base of this to ground. Now I might have that hooked up to the wrong ground. It might need to go to this end. I'll work that out under load, because it will work differently under load if I've hooked up to the wrong end. That'll be easy to work out. But when I turn this on, the base of this transistor and the base of this transistor, when I turn the base of this transistor on, it pulls everything down from here to ground, perfect, and I'm only left with the reference current flowing out the output terminals. When I turn this transistor on to turn this one off, it doesn't turn off all the way. So I've got to work out where there's obviously current paths that I haven't thought about that are not allowing this to be biased off all the way. Now I've thought about two ways of doing it. Incidentally, this is the board I had in there. Basically, those are the two transistors with the inverting pull down setup and some protection diodes across the emitter to emitter on there. Anyway, either I've got to turn some transistors around, bias them differently, or stick a PNP in somewhere, or the other idea I was thinking is use a MOSFET, like this is 2N7000 in here. I can do that, but I need to bias it so it's in a linear region. It doesn't matter if the constant current circuitry can pull it out of the linear region and just turn it on hard or turn it off. That's fine. But when the constant current, you start to turn the constant current down, up, or you put the power supply into you start going closer to constant voltage mode, is what I'm trying to say. You can't have that FET be completely open because the reference voltage needs to be present there on the base terminal. Because otherwise, if the reference voltage is not present at the base terminal here, when the power supply tries to go from constant current to constant voltage mode, your compliance voltage will not be where you set it. So I hope that makes sense, but that's the conundrum I'm at right now. This is the thing about circuit design. You have to work stuff out. I just want to point something out in this video too, because the last update I made on this, someone commented saying that I could have built my own supply by now and just pilfered the parts from the old one. I just want to point out, this isn't the old one. I don't know, I'm a bit confused by what you even might mean by that. I got this really old supply and I modified it and restored it, and it works beautifully now. There's nothing wrong with it at all. It works perfectly. Dual tracking, the whole lot. So, been using it for weeks. It's great. I've got this dual supply. I've got this single supply. I've got this one that I am designing from scratch in my spare time. I don't have much time on it. That's why there's only little updates here and there. I've got this project that I'm making into an adjustable supply of a panel meter and all that. I've got this modified switch mode board that I'm either going to use the same board or I'm going to rip all the parts off of it that I need and make a slightly beefier switch mode power supply because I want a high voltage switch mode supply. I also have this box down here. This is to build two channel microcurrent supply. So in terms of supplies, there's going to be, I haven't decided whether I'm going to do that in two boxes, like two separate microcurrent supplies, or two in one, but two microcurrent supplies, 16, maybe 20, 24-ish volt supply, this supply, that supply, I'm counting on my other hand now, the other supply and the other supply. That's 7 supplies. That's a load bank, by the way. So just if you're a bit confused, no, I have heaps of supply projects going on here. That's probably why it's so confusing for you. But no, I'm definitely finished on that old one, and that's going great. This is my own design. I am designing this completely from scratch, and I set myself some criteria to not use other people's designs, to try and make it all transistor based, really low noise, really high response times. I set a lot of design criteria on this, so yeah, and I don't have a lot of time to do it, so I just get a little bit of work done here or there, you know, like today I've got a couple of hours, so I've come in to play around with it. But yeah, just to make that clear for anyone else that might be confused, no, I'm not spending weeks on the same supply. This is my one that I come back to every so often in between doing other things, and the last one I was working on is already finished. The two brand new ones that I've got there on the bench set up, they have got their own problems. The switching one, when it's in constant current, the current's all like flicky. If it's trying to run constant current mode into a resistance of, you know, like not a hard load like 10 ohms or 20 ohms, but you know, 100 ohms, 200 ohms, the constant current sort of flicks. If you put it on an analog meter and look at it, you can see it going like this. And it's got a lot of common mode noise and ripple on the output. Same with the other one I've got. Also the other one I've got, the linear one, dual tracking, it's got extremely inadequately sized heat sinks. So I've got to do a couple of jobs on those supplies too. The switching one, I've probably got to do something to the feedback circuitry and put some snubbers on the switching devices and whatnot. The linear one, I've got to, and probably add a common mode network to the output terminals. Same thing with the linear one, common mode output network. Have a look at what they've done for noise suppression in there. Increase the size of the heat sinks. So yeah, you know, like there's always, well, not always, I mean, yeah, always will be from time to time, but for the next few months, there's going to be a lot of power supply projects that I'm coming backwards and forwards to, if that makes sense. So I hope that clears everything up. So I'm going to continue on this now. I'm going to try and work out, I was trying to measure it in circuit, and all I could tell was that when I turn this transistor on, which is the weird thing, because I thought maybe I wasn't turning it on all the way. and that wasn't the problem, because if I put my tweezers across the collector to emitter, which turns this transistor off, which was biased with this resistor to its base, that resistor, if I turned it hard off like this with my tweezers, there was still a voltage drop across it that wasn't the complete reference voltage. So it should have, when the power supply is turned up to full and you open that and then measure the voltage between the two, it should be about 34 volts, because it'll be the reference voltage plus whatever the output can go up to if you open the base here, which it's about 35 volts, maybe 32 point something, I can't remember. But anyway, my point is, it was like a 5 or 6 volt drop across it. So there's something funky going on there. I tried a lot of different things to try and get it to work. So that's why I'm thinking I might have to do, like, invert some of my circuitry of a PNP and NPN setup to avoid a current path. I've got a funny feeling I've got current going out a base terminal and into another transistor or something like that. Or MOSFETs, insulated gates, right? That's the other way of doing it. But like I said before, putting a MOSFET in here, like I said, if it goes completely open, then there's no constant voltage feedback. And then if the constant current circuitry starts to pull up, not pull down this transistor, and it leans back towards constant voltage, there's going to be no compliance voltage limit or feedback for that matter. So the MOSFET will have to be biased in its active region. So when the constant current circuit tries to turn this transistor on and this transistor on to pull the MOSFET down, which is what I'm proposing to replace this with, it can't pull the MOSFET all the way off unless it's in constant current mode, like completely, to the point that the current is drawing the output voltage down more than, you know what I'm trying to say. It can't get to the point where it goes back to constant voltage and then the voltage goes up because there's a broken path here. So I've got a bit of thinking to do, but I really, really, really want to make this circuit work, because the other way around it was to make this is how I originally designed this. It was I came up with two designs, one with op amps and one where I basically built a op amp for, like just a current mirror, a current source, a long tail pair, diff pair, whatever you want to call it, all slammed together, and that was my comparator. And then I had a driver transistor feeding into a driver transistor, or comparator, whatever you want to call it, error amplifier. And then my constant current circuitry was the same thing, but to measure the current shunt, I built a super transistor on each side, and I got okay performance sometimes, and other times it seemed a bit funky, and I don't know if it was because it was on breadboard, or I think it was, so yeah, anyway, that's the whole idea of this project. I've ended up deciding to go with my own design transistor, and because I got such good what do you call it, regulation with the one, if you take out this and this, the floating reference, the regulated supply, and that comparator transistor, and the way it's wired up between the two terminals, is what gives it amazing regulation with just one transistor. And yeah, obviously there are some diodes that go from here to the base like this to stop reverse base emitter voltage if a spike comes in a negative terminal. It's a 4148 and a 3.6 volt Zener, so it stays out the conduction range. Doesn't affect temp code, but does clamp well before a spike would break down this junction. And then the same for this transistor, I'd done the same, which is what I just put 4 diodes in there. Actually, yeah, no, I went back to the 4 diodes method for the other one too. I did have a Zener in there, but I went back to 4 diodes. It does affect thermal regulation, but it doesn't affect performance. And for that reason, because I'm planning on ovenizing stuff in here, I figured, well, if it only affects thermal performance, not regulation, then I'm happy to use 4 1/4/8 and a Xena, because probably, you know, putting 10 of them in there is probably cheaper than one Xena. You go and think about it, the Xena's going to be a couple bucks or $1 something or whatever. These in a pack of 100 even work out to like a cent each or something, you know. So it just doesn't make sense unless this was needed, but it's not, because I can build up, you know, enough voltage there to keep it out of the regulation area, the voltage, the junction voltages basically. But I can give protection at the same time, and you know, it clamps quick enough like that too, obviously. So yeah, all right, so I'm gonna go play with this now, enough wafting on. I hope that makes sense. That's why I've kept this piece of paper, so people can stare at it and hopefully understand. Just for reference, this is positive out and this is negative out, and this is common, and this is positive. These 2 points go back to the main capacitor bank that comes off the relay taps. This regulated supply comes off one of the transformer windings, but its ground is going straight back to the common. That's how all these rails are referenced to ground, even though it's a regulated supply that's not running off that terminal there. So I hope that clears up a few things, and the fact that that's floating, I hope that makes sense. But yeah, so I'm going to have a look at trying to use different transistors, so NP and PNP arrangements, and a MOSFET, and I'll report back with where I get to. But basically the problem I had, like I said, is I couldn't get it to turn off all the way, so I could get the output to go down to that 28 milliamps or whatever, which is just literally being passed through a base junction of a transistor from the reference, which is really, really bad. Because it's going like this, it's going, you know, ignore that. It's going through this base junction and out the output terminal. So that's like 30 milliamps going through a base junction. That's not good, especially at like 30 volts, you know. Yeah, so I've got to work a few things out here. All right, I'll be back in a sec. All right, so after much playing around, I've ended up trying all sorts of things with optocouplers and 4 and 25 optocouplers with the base output, and pin out, you know what I mean, PNP arrangements, NPN arrangements, mixtures of both. What I ended up doing was taking the 1K current sourcing resistor off the reference there and replacing it with a 33K, because with the voltages that are there, that means that with this transistor turned hard on and the output turned hard off, at 30 volts a maximum of 1 milliamp can leak out from the reference. However, under a 5 amp load, instead of 9-10 millivolts of error, there's now almost 15 millivolts of error. So what I'm going to try now is Darlington pair this transistor. Now if I do that, it increases the VBE by twice, which means the minimum voltage that you can turn this down to will increase by double. But I think I've got a workaround for this. When I ovenize it, right, and don't worry about the slow response, it's just because I've decreased the current and I've just removed some capacitors. There's still a whole microfarad there going through a 33K resistor. I've got to change the value of those capacitors. Even that one capacitor is too big. Okay, 0.719. That's with Oh yeah, it's because it's got a 33k resistor. Yeah, see, the smaller the value of resistor, the lower it will go to. Let's just see. Let me just heat up that transistor and see. Oh, what the hell? What just happened there? What? What's causing that? Oh, I've got a loose solder connection there. Huh, okay. That explains why the voltage was a little bit high too. I gotta go redo that solder connection and then I'll just reshoot this scene again because that could be why the regulation's off. But what I was thinking is if I put a Darlington pair there, okay, this voltage is going to double, but when I heat it, it's usually around there, 600 and something, 550 to 650 millivolts. That's going to be roughly halved when it's ovenized. So even with two in a Darlington configuration, that's still only going to end up being about 550, 600 millivolts. I'm pretty happy if I can turn the supply down to that lower voltage. Like, it doesn't need to go down to 1 millivolt for me. The thing I'm more concerned about is the current accuracy and the actual accuracy of the voltage, like the deviation. Like, you know, I'm happy that it doesn't deviate by 1 millivolt at the bottom end. By about 10 volts, it deflects like 1 millivolt. By the top end, it's usually about 7, 8 millivolts. At the moment, it's 15. Anyway, I'm getting there. So, yeah, I'll sort out this soldering and I'll be back in a sec. Alright, I found something that works. I can cut the output current completely to zero. So if I connect the base of this transistor to its collector, turn it on, with the supply turned all the way up to 30 volts, there's about 25, 26, I can't remember, 28, something like that, milliamps on the output. What I've done now is this is an NPN transistor, but it's round the other way. So its collector is going to the base of this transistor. With it wired up like that, I don't need diodes across it either for protection. Also, I don't have a transistor pulling its base down to the negative rail, causing another path for the current to flow to negative, because that's what's happening through the base of that transistor originally from the reference. So that solves two issues just by turning an NPN transistor around the other way. Doesn't affect regulation, still gets biased from the same point with a 470k resistor. So, how does this work? Well, when this transistor, this second one, gets turned on, the current drops to around 25 milliamps. And then when this is open, also because it's around the other way, it doesn't need a pull down resistor to turn it off completely. It's guaranteed to turn off like this. All you need to do is open that connection or vary the voltage to it with another transistor, and that removes the reference current, leaving a net zero current at the output terminals. So now I've got to come up with a method of basically opening this connection in a linear way, so not just open or shut, basically another transistor that is controlled at the same time as this transistor is controlled. And if I can pull that off, I'll be onto something. Can't remember if I pointed this out before or not, but I put the 1K resistor back in there and all the caps back in, screwed the opto isolate. I don't think I made a video about that. I've been experimenting with a lot of different things. Anyway, I'll be back soon. Alright, I've already come up with an idea. What I'm thinking is if I now put a PNP transistor essentially in series with this resistor that biases this backwards NPN on, if there's a PNP in series with that, and I bias that PNP on with a negative source, obviously, it'll take a positive source to turn it off. Now, it'll also take a positive source to turn that off. If I can get these two controlled at the same time or referenced to each other in a way that I can get them to both be controlled in the linear region at the same time from the same positive voltage, then I've won. So I'm going to go try a couple more things now and I'll show you what I've come up with. Alright, I've finally done it. I'm going to end up getting, I've already got faster ones, but I'm going to end up using faster optocouplers just for the response timing of the constant current circuitry. But to be honest with you, transition frequency is just the thing switching from on to off. It's not when it's in the linear region, you know, it can work a lot faster like that. So these might even be alright. I'll have to do some calculations, but I've only got the single driver comparator down there. What I've done, I've still got this essentially back to front, like the collector of this transistor goes to the base of the comparator, and the reference goes to, the reference is negative, goes to the emitter of this, right? So it's round the other way to how I had it before is what I mean by backwards. Which makes sense for this circuit. Then there's a 470 kilo ohm resistor going to a PNP transistor. Up here. I know it's not very clear, it looks like the legs are touching, but they're not. And then the other side of that transistor, its emitter, is going down to the power rail from this board. So power can only pass through this transistor when it's biased on with this negative, from the negative rail through this 470k resistor. However, if you collect its emitter to its base, because it's a PNP, it turns it off. So what I've done is I've put an opto there and another opto across the collector and emitter of the comparator. Now when you turn both the optos on at the same time, what happens is the reference voltage gets pulled away from, or it gets open circuited here, and the comparator goes hard on pulling the output down. Now what I'm going to do is I'm going to add some resistance in between these two optos so that basically this one doesn't come on as hard as the first one down there, so that as it's coming out of constant current and back into constant voltage mode, there's no current spikes or voltage spikes because the voltage reference is out of circuit still, for example. We always want this opto to be turning off before the one down there, if that makes sense. Well, yeah, but I've done it. So now I need to remake up this board down here to house all of this, which is one opto, two opto, PNP, NPN, two resistors. Might need some other things. I haven't put a scope on the output to see what sort of noise this is creating. I might need to add capacitors and snubbers, or there could be more still. So I definitely need to etch a new PCB, and I've had problems with the etching stuff I got at the moment, so I'm going to order some ferric chloride. Might grab a few other things too, but I guess I'm up to where I'm up to right now. I'll give you guys a quick demo. I'll apply some power from an external source to the LED side of the two optos. The reason I say external source is because the constant current circuitry will be running off one of these flybacks, so it's not actually powered from the circuitry in here. So it's completely isolated on both sides now because its power source is a flyback, so it's isolated. Its output goes into an opto, so it's isolated. The only point in which it'll have, you know what I'm trying to say, the only point it'll come in contact with this circuitry will be the current shunt, just across it. So yeah, I'll just reset up so that I can demonstrate this. I'll be back in a sec. Alright, so without even a resistor between the two optos, so they're just switching on at the same time, which is not how this circuit should behave. I've got the voltage turned up all the way. I'll prove this. Sorry. I'll prove this to you. See, I've got this powering two optos. So if let's use the current knob. Alright. Now I'll get my hand on the voltage. See, I've got complete control of the current from way over what the power supply is designed to do, all the way down to 0. Let's turn it up a little bit more and it's at 0. Oh. I'll be happy if there's half a milliamp or a milliamp there. I really don't care. Like I said, I wanted it to go down to 1 milliamp. That's, you know, I'm happy. So this is going to be my circuit. I'll draw it out on some paper so it makes sense for you guys now, and I'll have to order up some solution. Yeah, there's nothing coming out of there. There isn't even voltage until I turn this down. I'm just turning it down very slowly. That's going to work perfectly in the feedback loop with my constant current circuit. And the beautiful thing about it is, like I said, as long as I make sure that, how do I explain this? This opto down here sees, now I've got to think about this. This opto here just needs to see this current. So it's basically, I'd be powering it from this opto and have a resistor in series with this opto, with both the optos in parallel. It's that simple. And all I need to do is basically make sure one opto is like 5-10 milliamps ahead of the other on the LED side. I've already worked the math out on how this is going to work. It just ensures that when, like I said, as the constant current, the output of the constant current comparator comes down, what's controlling these op amps, it just ensures that this one is the first one to turn off, leaving the reference voltage there, because if the reference voltage was open circuit, the output voltage could shoot up higher than your compliance voltage that you've got whatever your voltage set to before you set your constant current compliance voltage. So yeah, I'll draw this out on paper now that I've shown it working, and like I said, I can't really do much more on it until I get circuit board, so we might start on one of the other supplies. I've noticed a couple little quirks with that thing, nothing major. That, big quirks, and that, it's just a horrid design that needs to be improved. But I really want to get started on this build here too, so it's an old CB power supply. I want to convert into a bench supply. Anyway, I'll draw this out on paper now, because yeah, that really evolved. That's the thing about prototyping. And I know it looks like a mess, but again, prototyping. Like I said, you can't do stuff like this. You know, could you imagine having the relays chattering around and, you know, short on the output and it going to full current, no current because you've got loose connections on a breadboard? Like, you can't do that with this sort of stuff. Same thing with accuracy, you know. So, yeah, end up just soldering it all together. Got it, you know, adjusting values and whatnot until it works, and I'll draw the diagram out, make up a board and etch the board, mount everything to the board, and we'll move on. We're actually up to the constant current circuitry. It's the next thing to be done on here because the thermals are good now. This thing's sorted out, so it's not spewing noise into here. The panel meter can just be run from a floating supply, so I'm not worried about that. And this was the only other thing I had to sort out, so not too far from being complete, this thing. Alright, I'll get this drawn out. Alright, so that is that is basically the, you know, like a block diagram. I'm not going to sit there and draw the entire 36 volt regulator circuit, the tap changer circuit, that's a bridge rectifier. You know, I'm not going to draw all 5 capacitors. I'm not going to draw the 2 transistors and the emitter resistors and the base resistors and the entire Darlington array with its protection diodes and the output protection diodes and the base to emitter resistors and decoupling capacitors. You know, like, I've just block diagrammed a lot of things, you know, Darlington array times 2 output devices, you know, discharge, cap, rectifier, tap changer, transformer, 4 taps, the what do we got? 0, 10, 24, 38. Right. Okay. Floating supply for the adjustable reference. Current shunt, you know, typical output capacitor, discharge resistor, anti-parallel diode. There's also a common mode network on the output. Capacitor going from each side to a common point with a resistor going off the ground. But anyway, that's not what we're here to talk about. There's heaps more in there too. There's 4 4-wire outputs and 2 4-wire switching and panel meters and fan control circuitry, and there's heaps in there. But for the purpose of this is the important part. What I had before, maybe I should get another pen. Something that's light. So before, if you could just imagine that transistor was just bypassed with that link, and that optocoupler, this resistor I haven't worked out the value of yet, you know, these 2 resistors, this transistor, none of that's here, you know. the reference used to just go boom straight into this transistor. So now what I've done is I've put another optocoupler, the transistor in the optocoupler in parallel to that. So when you turn the optocoupler on, it pulls down the output, right? But we still have the problem of the reference current flowing out the reference through the transistor's base and out the output. So what I've done is I've added a transistor here, which is have I drawn something wrong here? I'm really bad at drawing schematics. My apologies. I just get the feeling I've done something wrong. Done something silly. Oh no. Yeah. So through a PNP transistor, this transistor's biased on with a 470k resistor. So it's always on, and that comes from the regulated supply over here. However, there's an optocoupler also across this PNP transistor. So when you short the emitter to base of this PNP device, it pulls the current away from this 470k resistor, and this turns off. Once this is open, there's no current able to flow out the output terminals from the reference. Caveat with that is, if both these optocouplers were to be running the same current and switching at the exact same time, what would happen is, as it goes from constant current mode to constant voltage mode, the reference would still be disconnected via this transistor, and the voltage could go up higher than the compliance voltage. So my workaround for that at the moment is just a resistor. So basically your constant current circuit, which is, it's going to monitor the shunt. Makes sense. It's going to monitor the shunt, and then these two terminals are going to go to the current set, right? And what's going to happen is it's going to be able to, I might have put the resistor in the wrong spot. Let's see. Yeah, I put the resistor in the wrong spot. Actually, I can fix that. There we go. That works. So this opto sees more current than this one, meaning as the constant current circuitry starts to pull up on its current, like it starts to go closer to constant voltage mode again, and these optos start to come open or out of regulation, i.e. no LED driver current, the one up here, it's gonna turn off before this one. We want that to happen so the reference voltage gets restored before this is open, and then the compliance voltage shoots up higher than what it's set. I hope that all makes sense. The circuit's there, so you can stare at it for a minute. You can pause it if you want and stare at it and try and work out what on earth I'm on about. But all I've got left to do now, I know for a fact that this transistor and these 4 diodes need to be ovenized. I have not thought about anything else yet, so I know that transistor is going to have to be ovenized. I'm going to have to work out a few things in here are going to have to be ovenized too, because it's not just going to be this that affects the regulation. You see, things outside of the actual regulator itself that are in the feedback loop, they won't affect regulation so much because the gain of the regulator makes up for that. But if the regulator itself, the comparator transistor, something that's in series with the reference, if that changes resistance, the reference voltage is going to go up or down, which is going to change the output voltage. Those are the things that I was talking about when I said I want to put however many components it ends up being. They're going to be put into a little block and heated. Anyway, I hope that explains everything. That's where I'm up to at the moment. I'm probably not going to get anything done for like another week on this. I might, who knows. I've got to etch up a circuit board. I've got to work out the value of that resistor, do some more testing, but as you saw before, just with the two optos tied together, it was already behaving pretty well perfectly. So once I add that resistor in there, you know, I'm going to have really smooth control of it, and the constant current circuit will love that. Until I get ferric chloride or something to etch with, I won't be doing anything because, well, I can't really do much more work on it with all this just, you know, hovering in the breeze. So all of those components that are on that board and these components, plus the missing resistor, plus whatever capacitors I have to put on these transistors for compensation, I've got to work all that out, make it up on a board, etch the board, and take that board out, and the new one will go there. So that will be literally the next video that's on this power supply build, is when I make that board up. So that's all for this video. I'm going to leave it for here because I literally can't do anything until I get the stuff to etch the board up. I hope everyone understands. I've tried to be a little bit more clear, include a few more things to try and help it make sense. Just one thing to note, that I guess this is probably common sense, but for those people who don't know, the tap changer gets its sense off the positive terminal. Tap changer is also referenced to the 0 volt rail. I hope that makes sense to everyone. Incidentally, like I was saying about there being all these different things that run off the output, such as a load resistor, sense line that goes to tap changer, it goes to the reference, it goes to panel meters. I've got a resistor in line with all this stuff, and that also goes off to the current circuitry. The leakage current across that resistor gets deducted from the measured current, and that's how I get an accurate current measurement. Alright, thanks for watching. Again, I hope this made sense, and I'll see you on the next one. If you like my content, please remember to like and subscribe. I'm a new channel and I need the help to grow. Thanks everyone. Sorry, just one more note that I forgot to point out. By using a PNP transistor here and having an NPN turned around the other way, I was able to still obtain 0.560 volt at the bottom end, as far down as it can go, without it being ovenized. And say that's it ovenized, it'll probably be around there. It'll probably go down to 350 millivolts, which is fine for me. I'm happy with that. Also, just in case no one believes it, with all of this added on to the driver circuitry, you're probably thinking that it's lost precision. I've spent a long time doing this. I've got to wait for this bloody transistor to cool down. But I just heat it up. I'm just going to turn the light on. 30.171. I think it was actually somewhere around here. I'll just wait. Yeah, there you go. Alright. Light on. 10 millivolts at the top. And this panel meter is 1 millivolt out, so it deflects a millivolt when there's no millivolt of deflection on the output. I've proved that in other videos. I put my multimeter across the terminals. It's because the panel meter is running through this 1 ohm resistor and there's volt drop across that, because there's so many things running off of it. Again, 1 millivolt. So, I didn't lose regulation. And I can now put my constant current circuitry in there. Alright, thanks for watching. I'll see you on the next one.